Welcome to part two, modelling options and the MAIHDA approach. I'm George Leckie from the University of Bristol. So we're going to walk you through the actual statistical models underlying the MAIHDA approach here. And we're going to contrast that with some simpler linear regression-based approaches. So let's get going. So remember, what we're really interested in is how individuals' outcomes vary across intersections, where these intersections are defined by combinations of individuals' social identities, maybe gender, maybe ethnicity, maybe social class, and so on. Okay. So the simplest kind of analysis that people would do in that situation would be to run a linear regression model. So we're going to go through three approaches or options here. So the simplest thing you might do is the equation given here. So suppose the individual outcome of interest was individual health, might be something like body mass index or something else. We do a linear regression of that on the social identities of interest, maybe gender in this example, maybe ethnicity, maybe age, and so on. And you'd be able to estimate the main effect of each social identity having adjusted for the others. Okay, that'd be one way to start to study differences in the outcome across social identities. Okay, so that will tell you the effect of each social identity in isolation, but it's not really directly speaking to how combinations of these social identities lead to a kind of complex mapping of individual health outcomes. So we're losing some nuance here. This is a bit blunt. So to make that clearer, let's go back to the graph that Andy showed in the previous presentation. Essentially, what we're doing here with a traditional linear regression with main effects is the analysis on the left. Okay, and I might even get my my little drawing crayons out here. Okay, so we've implicitly done this kind of analysis. Okay, but what we're saying is that often the truth might be more nuanced and more complex. And particularly when you are trying to speak to particular intersections of social identities, you want to make statements about the experiences of, for example, Black women versus white women, and Black men versus Black women or versus white men. When you want to do that nuanced description across intersections, you really need to at least explore whether the patterns which are really out there in the real world are more complex than what a naive main effects analysis would suggest. And of course, in this particular example that Andy talked through at length, there were distinct differences. Really, it was only Black women who had distinctly different outcomes from the other three groups, which is the plot on the right, whereas the simpler analysis would be misleading because it would suggest that white women had different experiences from white men, and that Black men had different experiences from white men, when that was not the case. A more nuanced analysis would allow for that. So how do we do a more nuanced analysis? That's where we're going to next. So let's get rid of my children's scribbles. Shift on to the next slide. Okay, so this is what a conventional person doing linear regression would do if they wanted to allow for more nuance. Move from the plot on the left to the plot on the right on the previous slide. They'll put in the interactions between the social identities. Now, in our previous equation, we have three social identities. Okay, let's go wild with the colors. Let's choose a lovely orange color on this slide. So my three social identities were gender, ethnicity, and age. So with three variables, you need to put in the different interactions. You've got the two-way interaction between gender and ethnicity. You've got the two-way interaction between gender and age, and then you've got the two-way interaction between ethnicity and age, and then finally you've got the three-way interaction between gender, ethnicity, and age. And you can see, hopefully already, this is becoming quite a cumbersome model. Okay, imagine if we added a fourth social identity. There'll be further two-way interactions, three-way interactions, and a four-way interaction would be introduced, and so on. So very quickly, this approach of putting in all possible interactions becomes very hard for the researcher to interpret, very hard for the researcher, once they've worked out what's going on, to present the results in an accessible way to an audience, and so on. In more complex models, maybe you've got a count outcome or binary outcome. You know, some of these cells are pretty small. It all becomes a little bit unstable and noisy, and so on. So really, there are limits to the conventional chucking and interactions approach here, is what we're saying. Okay. Also, you get many terms relating to small pockets of the data, and so we're at risk of multiple testing issues where we find false positives. We find an apparent pattern going on in our sample data, and we conclude, right, that must be going on in the world at large, when in reality it's just some kind of peculiarity in our small data. Okay, and we're doing many parameter tests here, many coefficients. Of course, certain things pop up, and so we ideally would be a bit stricter. So that kind of concerns us. Okay, so what happens is the researchers, they see this and they balk, like, let's pull back, let's not get so complex. So one way to pull back, the researchers will typically do, is that they'll just kind of focus on one, often two-way interaction of interest, maybe gender by ethnicity. They'll ignore any potential interactions with age and any other social identities in the model. And this might be theoretically informed, okay? And so it contrasts the saturated approach up top. So that helps kind of make things simpler. It kind of helps kind of reduce the risk of the multiple testing issues because there's less parameters going on. You're cutting up the data less fine as well, as it's less noisy. So there are positives in this, but the problem is, you know, what if you're looking for the wrong interaction? You know, maybe the true interaction is one between ethnicity and age, and you're just not even looking for it now. So we kind of want to combine the features of both these approaches in a way. We want to kind of explore everything, which is what the top approach does, but we want to have some kind of a simpler way of doing this and some kind of control over multiple testing, which is what the bottom equation does. And so that brings us neatly on to MAIHDA. Okay. So MAIHDA essentially consists of two separate two-level linear regression. So it's a direct extension of conventional linear regression to two levels. This is what multi-level modeling is. But it's going to be unusual because whereas in multi-level modeling, you'd often think of, hey, I've got students nested within schools. Hey, I've got individuals nested within areas. Hey, I've got patients nested within hospitals. Here, the individuals in question, they're not nested within an institution or a geographic area. They're nested within their intersections, okay? And those intersections are defined by combinations of social identities. So the first intersection might be white male, middle-aged, middle income, okay? And then you cycle through all the permutations. Later on, you might have a white female of high education, but low income. And later on, you get different ethnicities and so on. Each of those is treated as a cluster, as a level 2 unit or grouping. Okay, so the two models that you fit, and let's cycle over all the exciting colours in the palette here. Let's go for a nice pink. So we're modelling once again the individual health outcome, perhaps BMI of individual I in intersection J. Okay, and everyone in that intersection is the same as you. They have the same gender, the same ethnicity, the same education, the same income, whatever it is. And then we're regressing individual health outcomes on beta 0, an overall intercept, which will estimate the overall average health across all individuals and all intersections. And then we're going to have the random part of the model. We've got UJ, which is a random effect. Okay, going to capture how the mean outcome for each and every intersection, J, deviates from the overall average beta 0. So some intersections, just in general, people have better health than the overall average. Other intersections, defined by different combination of social identities, individuals just have lower health than average. And we're interested in those differences in average health across the intersections. Those are the inequalities of interest. Now, of course, within a specific intersection, you've got lots and lots of people. Yes, they've got the same gender as one another, the same education, income, and so on, and ethnicity, but they're different people, and their individual health will vary around their intersection average, and that's captured by EIJ, which is the level 1 residual. Okay, so so essentially that's the first of the two MAIHDA models. So what we do is we define the intersections. That generates a new variable in our spreadsheet of data. We treat that as the level 2 units or clusters. We fit a 2-level regression of health on only an intercept, and what we get back is a breakdown of individual health outcomes into the overall average, an intersection effect, and a residual. And crucially, those intersection effects, we estimate this new parameter, sigma u squared, which is the variance in the mean outcomes across intersections. That parameter quantifies how big are intersectional inequalities. And we put that in perspective by comparing that parameter to the variance of the residuals, the extent to which individuals vary around their averages. So we're interested in the relative magnitude of sigma u squared, okay, the variance in the intersection means. And that's actually going to give us a statistic called the variance partition coefficient, which we'll mention on the next slide as well, which is like an effect size, how big are intersectional inequalities. It's a statistic which ranges between 0 and 1. The bigger the proportion, then the higher the proportion of the variability in individual outcome, health, which lies across intersection means versus within intersections. And so that's a nice statistic to compare across studies, across countries, or across outcomes and so on. It's an effect size metric, essentially. Okay, so that's the first kind of step of the analysis, which is just to quantify the importance of intersectional inequalities by fitting this model and calculating that VPC. Once we've done that and established, hey, there are these big intersectional inequalities, we then move on to the more nuanced question of, well, to what extent can those be characterized as simply due to the additive risk factors, okay, of the social identities? That in general, females have higher health. In general, people of lower education have lower health, these additive main effects, okay? Versus, to what extent are there interactions between social identities? So what's the relative importance of additive risk factors versus non-additive interaction effects in explaining the inequalities? So let's do that. I'll bin my drawings, I'll jump on to the next slide, and let's have a look. Let's get the pens out, change the color to what haven't we had yet? I don't think we've had turquoise, or ice blue, as Zoom calls it. Okay, so we have two models. Model 1 we've already fitted. That was the 2-level regression of health on only an intercept, where we got out the intersection random effect and the residual, and from that got the proportion of action happening between intersections. Model 2 is the new one, where we have the same outcome, individual health, but now we regress it on the additive main effects. Okay, and in this model, we have a dummy variable for sex. So maybe this is a dummy variable for being female versus male. We've got 3 ethnic groups, for example, and so we put in 2 dummies for those to contrast, let's say, Black individuals to the reference category white, perhaps Asian individuals contrasted to the reference category white. And then we have education levels. Here you can see mid-ed and high-ed have gone in, so obviously low-ed has been left out. So we've got 3 education levels, and there'll be an education gradient in health, which will be captured by those betas, just like you get in linear regression. And perhaps there's an age gradient as well. And so we've got low age, which has been the omitted variable, mid-age and high age, and we'll get the age gradient. So from that, you can get the kind of the additive main effect, the additive risk factors on health of these socio-demographic characteristics. Okay, so that part of the model highlighted in blue is capturing, well, to what extent are inequalities due to additive effects. The UJ is again the intersection random effect. But now this random effect is picking up conceptually all possible 2-way, 3-way, and 4-way interaction effects. Okay, we've got 4 social identities in the model: sex, ethnicity, education, and age. So if we were to put in all the interactions in the conventional way, we'd get up to a four-way interaction. But that one term uj is soaking up all of that. Now, every intersection has its own value, and we can predict these post-estimation and study them. And so it's a different setup to conventional regression, where you have lots more terms in the model, lots more betas. Okay. So the uj now is capturing those interactions, and so the sigma u squared, that parameter is reduced from model 1 because we've stripped out the additive main effects, that's come out of the model, and what's left in the sigma u squared is the variance of the interactions. Okay, and so we can use this magnitude to look at the relative importance of interactions versus main effects. Okay, we can essentially use it to say, well, what proportion of the initial variability we saw in model 1 is attributable to interaction effects, sigma u squared, versus in model 2, that is, versus the main effects. Okay, so you can look at the proportion, reduction in that parameter across the two models. And that's the second key statistic, which can be compared across studies, if the same studies done in different countries, for example. And then you can compare how that magnitude differs. Maybe interactions are more important in some countries, less than others. Okay, cracking. Let's shift on to the next slide. So those are the two kind of base models of a MAIHDA analysis. Of course, you can do much more, but that is the kind of the minimum analysis that people do. And so just to kind of to sum that up again, we'll get out. Oh, let's have a yellow. The first thing is you fit model 1, okay, and that allows you to answer how much do intersectional strata matter, or how big are inequalities? To what extent is the variation in individual health captured by mean differences across intersections? Okay, that is the VPC statistic, the proportion of variance level 2. Okay, standard statistical multi-level modeling, nice effect size. Okay, then model 2, we add in the main effects, the additive risk factors. We explain away the inequalities between intersections, because we say, well, they're attributable to these risk factors, but some is left over. And the sum which is left over is the part which is attributable to two-way, three-way, four-way interactions. And so we can calculate the second statistic, the PCV, which is to what extent have we explained away the inequalities, and that's the additive component, and 1 minus that will be the proportion attributable to interactions. So we get those two key statistics, but then we can go further. Okay, what we can do after that is we can use model 2 to predict the mean health at each and every intersection. And we get those model predictions with confidence intervals. We can do lots of graphical inspection of those mean differences, and we can use that to make effectively graphical league tables of inequalities. And we can do nuanced things to say, well, we can do a league table obviously in terms of mean outcomes, but we can do it also in terms of mean outcomes based only on the additive component, or we can rank intersections by the magnitude of the interaction effects. And interaction effects are capturing peculiar, unexpected behavior that you might miss from a naive analysis. And so you can see, well, which particular intersections is something peculiar going on, different from an additive main effects world, and then you can follow that up in further research. And so it's a nice way of identifying intersections where unexpected things are happening, which you would otherwise miss. So let's shift on. So there's going to be separate R practical and Stata practical video walkthroughs, which we're going to do later on, and you can pick and choose depending on which package you like. Andy will do R, I'll do Stata, but it'll be the same practical, and so you can learn. You can by looking at both as well. But here in one slide are the two models. Okay, so we'll go for a light purple this time. So if you're an R user, what you'd do is you'd use Doug Bates's LME4 package. You'd use the LMER function within that, which is the standard function for doing multi-level models, linear mixed effects regression. It's just a multi-level model. You'd regress the dependent variable health, and you regress it on an intercept, which is what the 1 is there, being very explicit, plus a random intercept across strata. Strata and intersections are synonyms. You can use one or the other in this literature. And so that allows the mean health to vary across the intersections. And of course, you've got a reference which data frame the data are in, and it's in a data frame called DF in this example. That's model 1, and we assign results to the object model 1. For model 2, again, LMER, again, the same health outcome. Again, we have an intercept, and now we add in the additive main effects for the social identities which were used to define the variable strata, which are sex, ethnicity, and education. And we'll put those into the model. It knows that those are categorical or factor variables, so we'll expand it to put in dummy variables for each, leaving one out as a reference category. And then we'll be able to estimate their regression coefficients to get the additive main effects. And it will again estimate those variance components, which then can be compared between model 2 and model 1. So if you're a Stata user like me, this is what you do. You use the mixed command for mixed models, which again is a synonym for multi-level models in Stata. The outcome here, well, it's written actually HbA1c. So I guess ideally we would have written health there just to make these consistent with one another. Yeah, that's just a typo on our part. By default, it will put in an intercept, and then to make it multi-level, that is to add in the stratum. Again, it says stratum here and strata there. Again, really ideally we'd write the same word. So strata, stratum, intersection, whatever you like, whatever the name of the variable is. We put that in there, and that will give the random effect and allow the mean health to vary across the intersections. Now, the default estimation in R is REML. The default estimation in Stata is ML. Okay, REML is restricted maximum likelihood. It's kind of preferred if you have a low number of clusters. In R, in Stata, it's ML, which is a bit more flexible. Just to make the two consistent with one another, we've switched on REML as an option in Stata. Second model, again, the mixed command, again, the same outcome, but now we put in sex, ethnicity, and education. The I dot just tells Stata explicitly that each variable there should be treated as a categorical variable and entered as a series of dummy variables or indicator variables, so I for indicator. So just to make that consistent with what we do. And then again, we have the stratum random effects, which will now be picking up the two-way, three-way, four-way interactions. And again, fitted by REML. So we have whole videos on how to do this properly, where we'll walk through obviously more slowly, but just at a high level, one slide, how you do it in R and Stata. It's just like any other multi-level model. Okay, the only difference is the clusters are not schools or neighborhoods. They are not a pre-existing variable in your data set. Rather, it's a new variable which you generate by the combinations of the particular social identities of interest, sex, ethnicity, education here. And that is the only difference mechanically in what we're doing. Last slide from me before I sign off this video. You might ask here, why not just use loads of dummy variables, the fixed effects approach? You could do a linear regression of health on a separate dummy variable for each and every intersection. Okay, so if you had 100 intersections, you'd have 100 dummy variables. Okay. Now it turns out that is equivalent to option 2 above. And if you cycle back a few slides, what you'll see option 2 was when you put a linear regression in between the variables of interest. I think they are sex, ethnicity, education, and age, and the two-way interactions and the three-way interactions and the four-way interactions. If you did that, both models fit equally because they're both saturated. They're just different parameterizations. Okay, so this parameterization described here, a separate dummy variable for every intersection, is more similar to the parameterization or the conceptualization of the MAIHDA model, where we're directly estimating the mean at every intersection, which is what dummy variables would do as well. But the key difference is, as well as not getting the VPs, the variance partition coefficients and the PCV, those two crucial effect sizes for characterizing what's going on and the magnitude of inequalities and their makeup, we're also not getting something else. which is that in the multi-level approach, the MAIHDA approach, the predicted intersection means are so-called shrinkage estimates, which pulls the very unreliable sample means for intersections, particularly rare intersections, towards the predicted means from the model based on the additive main effects. And this has preferred statistical properties. You can think of it as a smoothing approach to kind of try and deal with the noise. It also has Bayesian elements. We're borrowing strength. Okay, so our prediction for intersection 17 is not based just on the data for intersection 17, but it's dragging in information from across the distribution, because these intersections are all related. It's all part of a system. These aren't distinct islands. And if you're kind of a white female, high income, high education, that tells you nothing about another intersection, which might be white female, low education, low income, because there's things in common here, and that commonality is those additive main effects, and so we want to kind of utilize that. Now, chucking in a dummy variable for each and every intersection doesn't do that. It just treats each tiny pocket of data in isolation and calculates the mean. Okay, it's learning nothing from the system at large, whereas the MAIHDA approach does. So it sounds quite technical, but it's a really important point. Andy Bell's got a nice paper in 2019 where he does some simulation studies, which looks at shrinkage, also from the perspective of dealing with multiple testing. Clearly, if you have 100 dummy variables and nothing's going on, 5% of those will pop up as significant on average by chance alone, because we're testing at the 5% level. But in a MAIHDA approach, shrinkage will deal with that. So you don't need to kind of turn to Bonferroni corrections, which you might do in a conventional regression. There's kind of the shrinkage kind of gives an inbuilt conservatism by default, if you like, rather than having to worry about what kind of corrections we need to do to p-values. Okay, so lots of nice statistical advantages to the MAIHDA approach, as well as conceptual advantages as well. And that's it from me for this particular video. I'll be back to Andy next, and then you'll see me later on in this series of videos. So enjoy and good luck with your MAIHDA analysis.